Hello everyone, let's review the spring semester of the differential equations module. First, let's define Fourier transforms. For a function f of x, the Fourier transform f tilde of k is defined by f tilde of k is equal to the integral from minus infinity to infinity of f of x times e to the minus kx dx, where this integral exists. Now, let's discuss the properties of Fourier transform. We have the uniqueness property, which says for continuous functions, f of x equals g of x if and only if f tilde of k equals g tilde of k. We have the linearity property, which says for constants lambda and mu in the complex numbers, hx equaling lambda f of x plus mu g of x implies h tilde of k is equal to lambda f tilde of k plus mu g tilde of k. We have the translation property that for a constant a in the real numbers, g of x equaling f of x minus a implies g tilde of k is equal to e to the I k a f tilde of k. We have the frequency shift that for constant k naught in the reals, g of x equaling e to the I k naught x times f of x implies g tilde of k is equal to f tilde of k minus k naught. We have the scaling property that for constant a in the real numbers but not 0, g of x equaling f of a implies g tilde of k is equal to 1 over the modulus of a times f tilde of k over a. We have the derivative property that g of x equaling f dash of x implies g tilde of k is equal to I k f tilde k. We also have the factors of x property that g of x equaling x times f of x implies g tilde of k is equal to I times d f tilde dk. Next, let's discuss the transforms of functions of multiple variables. We can also transform functions of more than one variable, but we must choose which variable to transform on. For example, the transform of f of x and y with respect to x will be written f tilde of k and y, which is equal to the integral from minus infinity to infinity of f of x and y times e to the I k x dx. Observe that the derivatives with respect to the non-transformed variable are not affected by the transform. However, derivatives with respect to the transformed variable transform in the same way as for a function of one variable. Now, let's describe the Fourier inversion theorem. The inverse transform of a transform f tilde of k is given by 1 over 2 pi times the integral from minus infinity to infinity of f tilde of k e to the I k x dk. Let f tilde of k equal the integral from minus infinity to infinity of f of x e to the I k x dx be the Fourier transform of f of x. Where the inversion integral exists, we have that 1 over 2 pi times the integral from minus infinity to infinity of f tilde of k e to the I k x dk equals f of x if f is continuous at x and equals a half times f of x minus plus f of x plus otherwise, where f of x minus is equal to the limit as psi approaches x but psi is less than x of f of psi, and f of x plus is equal to the limit as psi approaches x where psi is greater than x for f of psi. The expression f of x equaling 1 over 2 pi times the integral from minus infinity to infinity of f tilde of k times e to the I k x dk, valid when f is continuous, is known as the Fourier representation of f of x. Next, let's discuss the convolution theorem. The convolution f convolute g of x of two functions f of x and g of x is defined by f convolute g of x is equal to the integral from minus infinity to infinity of f of psi times g of x minus psi d psi. Note that this is a metric in f and g, i.e. f convolute g of x is equal to g convolute f of x. The convolution theorem states that h of x equaling f convolute g of x is equivalent to f tilde of k equaling g tilde of k times f tilde of k, where f tilde, g tilde and h tilde are the Fourier transforms of f, g and h respectively. Then, let's state Parseval's theorem. Let f tilde of omega be the Fourier transform of f of t. Then, the integral from minus infinity to infinity of the modulus of f of t squared dt is equal to 1 over 2 pi times the integral from minus infinity to infinity of the modulus of f tilde of omega squared d omega. Now, let's discuss techniques for inverse transforms. First, there is direct calculation using the inversion theorem. Second, there is using knowledge of a forward transform and Fourier transform properties. Or third, there is using the convolution theorem. It says if our function to invert f of k can be written as the product of two functions, i.e. if f of k is equal to g of k times h of k, then the inverse is given by g convolute h of x, where g and h are the inverse Fourier transforms of g and h. Then let's discuss the application of Fourier transforms to integral equations. The method will only work if the integrals take the form of a convolution, and the function we are seeking decays sufficiently rapidly as x approaches plus or minus infinity. Next, let's discuss the application of Fourier transforms to linear ODEs. Fourier transforms can be used to solve inhomogeneous linear ODEs with constant coefficients. Suppose we have an equation of the form a d2y over dt squared plus b dy over dt plus cy is equal to f of t, where a, b, c are constants and f of t is a given function. Suppose also that the boundary conditions are such that y of t approaches 0 as t tends to plus or minus infinity. By taking the Fourier transform of the equation with respect to t, we find that y tilde of omega is equal to f tilde omega times g tilde of omega, where we defined g tilde of omega to be 1 over a times I omega squared plus b I omega plus c. Inverting, using the convolution theorem, we have that y of t is equal to f convolute g of t. Then we use partial fractions on g tilde of omega. Then we compute the inverse transform of each partial fraction and sum to find g of t. Next, we compute the convolution integral y of t is equal to the integral from minus infinity to infinity of f of tau times f of t minus tau d tau. Next, let's discuss the application to PDEs. Fourier transforms can be used to solve some PDEs. The equation must be linear, have one independent variable with range from minus infinity to infinity, and the solution sought must decay sufficiently rapidly as this variable tends to plus or minus infinity. The method is to transform the equation and the other boundary conditions with respect to the infinite variable. This will reduce the PDE to an ODE. We then solve the ODE and transform the solution back. Now, let's move on to describe the types of first-order PDE. Consider a first-order partial differential equation with two independent variables x and y, and one dependent variable u of x and y. The equation is said to be linear if it can be written in the form a of x and y times the partial derivative of u with respect to x plus b of x and y times the partial derivative with u with respect to y is equal to c of x and y plus d of x and y u, where a, b, c, d are functions of x and y. The equation is said to be semi-linear if it can be written in the form a of x and y times the partial derivative of u with respect to x plus b of x and y times the partial derivative of u with respect to y is equal to c of x, y, and u. Finally, the equation is said to be quasi-linear if it can be written in the form a of x, y, and u times the partial derivative of u with respect to x plus b of x, y, u times the partial derivative of u with respect to y is equal to c of x, y, u. Now, let's describe the rate of change along a curve. Suppose we have a curve defined parametrically in the xy plane, i.e. we write the curve as x of s, y of s for some functions x and y, with the variable s parameterizing the position along the curve. Then the value of u of x and y at the point s on the curve is given by u of x of s, y of s. The rate of change of u following the curve can be computed using the chain rule. We get du over ds is equal to d over ds of u of x of s, y of s, which is equal to the partial derivative of u with respect to x plus dx over ds plus the partial derivative of u with respect to y times dy over ds. Now, let's describe characteristics. Observe that in the special case where we chose the curve such that dx over ds is equal to a of x, y, u and dy over ds is equal to b of x, y, u, we have du over ds is equal to a of x, y, u times the partial derivative of u with respect to x plus b of x, y, u times the partial derivative of u with respect to y, which equals c of x, y, u. We have then transformed our PDE into three ODEs as dx over ds is equal to a of x, y, u, dy over ds is equal to b of x, y, u, and du over ds is equal to c of x, y, u. The special curves given by x of s, y of s are known as the characteristic. Given suitable boundary conditions, we can, in principle, integrate this ODE system along the characteristic to find the solution for our PDE. Now, let's discuss some results results for characteristics. In general, there is a characteristic passing through each point xy. Since dx over ds and dy over ds are defined by the equation at each point, the gradient is unique, and characteristics do not, in general, intersect. For linear and semi-linear equations, a and b do not depend on u. In this case, we can solve for the characteristic x of s, y of s first, and then find u later. Otherwise, the paths of the characteristics will depend on the value of u at each point, and hence also depend on the boundary conditions. Also, if c is equal to 0, then du over ds is equal to 0, so u is conserved, i.e. constant, along each characteristic. But note that u will generally take different values on different characteristics. Note that it makes sense often to eliminate s from the equations. We can divide through by dx over ds to obtain dy over dx is equal to b of xyu divided by a of xyu, and du over dx is equal to c of xyu over a of xyu. Or, alternatively, we could divide through by dy over ds to obtain dx over dy is equal to a of xyu over b of xyu, and du over dy is equal to c of xyu over b of xyu. Now, let's discuss boundary conditions and the domain of definition. The boundary conditions for PDE typically involve specifying the dependent function u, and or its derivatives, along subsets of the space of independent variables. For two independent variables x and y, the boundary conditions will be applied on the curve gamma in the xy plane. For first-order equations, we will provide a value either for u or the partial derivative of u in the direction normal to the curve. This is known as Cauchy data. We typically define the curve gamma parametrically, writing xy is equal to x of tau y of tau for tau between tau min and tau max for some given functions x of tau and y of tau. A boundary condition on u is then written by prescribing the values u0 of tau that u of xy takes at the point x of tau y of tau for each tau. We would write this as u of x of tau y of tau is equal to u0 of tau. To solve the PDE, we can imagine integrating du over ds along the characteristics in the xy plane starting from the boundary curve. The part of the xy plane that these characteristics reach is known as the domain of definition of the solution. The boundary conditions do not define the solution outside the domain of definition. Next, let's discuss the determination of partial derivatives from boundary data. A necessary condition for us to be able to solve a PDE in the neighbourhood of the boundary curve gamma is that we can uniquely determine all the partial derivatives of u at each point on gamma. For boundary condition u of x of tau y of tau is equal to u0 of tau that specifies the function value, we can test if this is possible as follows. First, the PDE itself gives a relationship involving the partial derivatives at the point x of tau y of tau on gamma. We have a of xy u0 times the partial derivative of u with respect to x plus b of xy u0 times the partial derivative of u with respect to y is equal to c of xy u0. Secondly, we can differentiate the boundary condition with respect to tau to obtain the partial derivative of u with respect to x plus dx over d tau plus partial derivative of u with respect to y plus dy over d tau is equal to d u0 over tau. These two equations can be combined into a single matrix vector equation as the matrix of a of xy u0, b of xy u0, x dash y dash times the vector ux uy is equal to c xy u0 u0 dash, where ux is equal to the partial derivative of u with respect to x, and uy is equal to the partial derivative of u with respect to y. The matrix and the right hand side are all known quantities from the equation and the boundary condition. This is therefore an equation for the partial derivatives ux and uy. We have a unique solution for ux and uy if and only if the matrix is non-singular, i.e. if the determinant of the matrix is not equal to 0, which occurs if and only if dy over dx does not equal b of xy u0 divided by a of xy u0. Since the characteristics have gradient dy over dx is equal to b over a, this is precisely the condition that the boundary curve is not tangent to a characteristic at the point xy. Now, let's discuss the application to first-order quasi-linear PDEs. With quasi-linear equations, we have the possibility of the gradient of the characteristics depending on the value of the function u. This means we cannot find the characteristics until we have found the solution for u, but we cannot find the solution until we have found the characteristic. The two must therefore be found simultaneously, making the solution much harder. The simplest case of this type of behavior has a equal to a of u p equal to b of u, and c equal to 0. Then the gradient of the characteristic depends only on u and not on either of the independent variables, and u is conserved along each characteristic. Then, although we do not know the path of the characteristic like before, we do know that they will be straight lines. The value of u, and hence the gradient, will be determined by the value at the initial or boundary condition. Next, let's discuss multi-valued solutions and shock. If different characteristics give different values, this means the solution is predicted to be multi-valued after a point, but rather than becoming multi-valued, the solution actually becomes discontinuous. This continuity is known as a shock. Characteristics are absorbed by the shock rather than passing through it, so they no longer cross. The position of the shock does not necessarily remain fixed, and it can move in space as time increases. Now, let's move on to defining dynamical systems. A dynamical system is a set of n equations in n variables where n is greater than or equal to 1, which give a rule for the development of the variables in terms of time, where time is greater than or equal to 0. We also know the initial state of the variables at time equals 0. The equation can be in terms of discrete steps in time, in which case we have a discrete dynamical system or a map, or time could be continuously varying, and we call them continuous dynamical systems or flows. In other words, the evolution rule is either a difference equation or a differential equation. Once the equation can be solved, given an initial point, it is possible to determine all future points, which would be its trajectory or the orbit. When f doesn't depend explicitly on time, the dynamical system are called autonomous systems. In the discrete case, we have then the 1D dynamical system x of n plus 1 is equal to f of x of n. They are also called difference equations or maps. Now let's discuss graphical analysis. We consider the one-dimensional system x dot equals f of x, where x of t is a real valued function of time for t greater than or equal to 0, with x of 0 equaling x0 given, and f of x is a smooth real valued function of x. If f is nonlinear, in many cases it is impossible to find a solution for this equation, so we will use graphical analysis. We will draw the phase portrait by plotting x dot versus x. The real line is then called the phase space, and a point x0 on this line is called a phase point. If t is the time, x of t is the position of an imaginary particle moving along the real axis, which started from an initial condition x0, and x dot the velocity of this particle. The function x of t is called the trajectory based at x0. The differential equation x dot equals f of x represents a vector field on the real line. Where x dot is greater than 0, x is increasing, and where x dot is less than 0, x is decreasing. Next, let's define equilibrium points. We define x star, an equilibrium point of x dot equals f of x, if f of x star equals 0. They are also called fixed points or steady solutions. If x0 equals x star, then x of t is equal to x star for all t greater than 0. Next, let's define stable. Suppose x dot equals f of x star is an equilibrium point, and x0 equaling x0 is given. Suppose that for all epsilon greater than 0 there exists delta greater than 0, such that the modulus of x0 minus x star is less than delta, implies modulus of x of t minus x star is less than epsilon for all t greater than 0, then x star is said to be stable. Then let's define unstable. The equilibrium point x star is said to be unstable if it is not stable. Then let's define asymptotically stable. An equilibrium point is said to be asymptotically stable if it's stable and there is some r greater than 0 such that the modulus of x of t minus x star tending to 0 as t approaches infinity for all x0 satisfying modulus of x0 minus x star is less than r. Then let's define globally asymptotically stable. An equilibrium point x star is said to be globally asymptotically stable if the modulus of x of t minus x star tends to 0 as t tends to infinity for any x0. Next, let's discuss linear stability analysis. For an equilibrium point x star of a dynamical system, we say that it is asymptotically stable if f dash of x star is less than 0, or unstable if f dash of x star is greater than 0. Next, let's define a hyperbolic equilibrium. An equilibrium point x star is called a hyperbolic equilibrium if f dash of x star does not equal 0. If f dash of x star does equal 0, then x star is called a non-hyperbolic or degenerate equilibrium. Now, let's discuss the existence and uniqueness theorem. Consider x dot equals f of x and x of 0 is equal to x0. Suppose that f of x and f dash of x are continuous on an open interval r of the x-axis, and suppose x0 is a point in R. Then the initial value problem has a solution x of t on some interval from minus b to b about t equals 0, and the solution is unique. Now let's discuss an observation. There are no periodic solutions to the equation x dot equals f of x on the 1D system. The trajectories are either forced to increase or decrease monotonically, or to remain constant. So in 1D, all trajectories either approach an equilibrium point or diverge to plus or minus infinity. Next, let's define bifurcations. The word bifurcation refers to sudden change in the qualitative structure of the flow when one of the parameters of the system is varied. For example, equilibrium points being created or destroyed, or their stability being changed. The parameter values at which these qualitative changes of the dynamics occur are called bifurcation points. Next, let's discuss saddle node bifurcations. This is the basic mechanism by which equilibrium points are created or destroyed. The typical example of the saddle node bifurcation is x dot is equal to r plus x squared. There are two equilibria if r is negative at x star is equal to plus or minus the square root of minus r. The positive equilibrium x star is equal to the square root of minus r is unstable, while x star equal minus square root of minus r is stable. There are no equilibrium points for r positive. Now let's discuss transcritical bifurcations. This is a mechanism by which equilibrium points change stability as some parameter is varied. Consider the differential equation x dot equals rx minus x squared. The equilibrium points are the solutions of r x star minus x star squared equals 0, or x star equals 0 and x star is equal to r. It is easy to show that if r is negative, then the origin x star is stable and x star equals r is unstable. If r is positive, then x star equaling 0 is unstable and x star equaling r is stable. There is an exchange of stabilities between the two equilibrium points as r increases through its critical value of r equals 0. Next, let's discuss pitchfork bifurcations. The equilibrium points appear and disappear in symmetrical pairs. There are two types: supercritical pitchfork bifurcation and subcritical pitchfork bifurcation. First, let's discuss supercritical pitchfork bifurcations. For supercritical pitchfork bifurcations, the typical example is x dot is equal to rx minus x cubed. The equilibria are x star is equal to 0 for r negative and x star is equal to 0 or x star is equal to plus or minus the square root of r for r positive. It is called supercritical because the additional equilibrium points are found when the parameter is above the critical value. Next, let's discuss subcritical pitchfork bifurcations. If we consider the equation x dot is equal to rx plus x cubed, we obtain the subcritical pitchfork bifurcation. Now, let's discuss an observation. To find a bifurcation point RC, we need to have a non-hyperbolic equilibrium point x star at the value r is equal to rc. This means that for a system x dot equals f of x, we look at the points where f of x star is equal to 0 and f dash of x star is also equal to 0. Next, let's discuss hysteresis. Consider the dynamical system x dot is equal to r plus x minus x cubed. For r equals 0, the equation has three equilibria, one unstable and two stable. The flow continues to have the same qualitative structure for r between minus r1 and r1, where r1 is the local maximum value of x minus x cubed and minus r1 is the local minimum value. For r equals minus r1 and r equals r1, the dynamical system is at a bifurcation point. For r less than minus r1 and r greater than r1, the equation has only one equilibrium point, which is stable. Then, let's discuss a fold or a cusp. We consider the dynamical system x dot is equal to h plus rx minus x cubed. The graph of this curve in the plane hr, also called the parameter space, is a cusp. On that cusp, there is a change in the number of equilibrium points from 1 to 3, corresponding to a saddle node bifurcation. We can draw a 3D graph in the hrx space by plotting the equation h plus rx minus x cubed is equal to 0. We get the cusp catastrophe surface. The term catastrophe is motivated by, as the parameters change, the state of the system can be carried over the edge of the upper surface, after which it drops discontinuously to the lower surface. Now, let's move on to discussing the analysis of a linear system. Consider a 2D linear system. X dot is equal to ax plus by, y dot is equal to cx plus dy, with a, b, c, d being constant. We can rewrite in the matrix form x dot is equal to mx, where x is equal to the vector xy, and m is equal to the matrix a, b, c, d. Note that x star equals 0 is an equilibrium point for the system. We are looking for the eigenvectors v1 and v2 of m corresponding to the eigenvalues λ1 and λ2. If we obtain them, then a general solution can be written as x of t is equal to c1 e to the λ1t v1 plus c2 e to the λ2t v2, where c1 and c2 are constants. The qualitative behaviour depends on the lambdas as well as the other constants. So we need to solve mv is equal to lambda v with v not equal to 0. The eigenvalues are given by the characteristic equation, the determinant of m minus lambda I equals 0, or lambda squared minus a plus d lambda plus ad minus bc is equal to 0. The solutions are λ1 and λ2 equals a plus d over 2 plus or minus the square root of a plus d over 2 squared minus ad minus bc. If we note a is equal to the trace of m equals a plus d, and d is equal to the determinant of m, we can write them as λ1 is equal to a over 2 minus the square root of a over 2 squared minus d, and λ2 is equal to a over 2 plus the square root of a over 2 squared minus d. Different cases will correspond to lambdas. If the lambdas are real and λ1 does not equal λ2 and they both don't equal 0, this corresponds to a squared being greater than 4d and d not being 0, and we have three subcases. If we have λ1 is less than λ2 which is less than 0, it corresponds to 0, 0 being a saddle node. In the AD plane, this happens when d is less than a squared over 4 and a is negative and b is positive. The solution approaches the origin as t tends to infinity, tangent to the slow eigendirection, which is defined as the direction spanned by the eigenvalue with smallest modulus. If 0 is less than λ1 which is less than λ2, the origin is an unstable node. In the AD plane, we need d to be less than a squared over 4 and both a and d are positive. The phase portrait is like the stable node, but all the arrows are reversed, pointing away from the origin. If λ1 is less than 0, but λ2 is greater than 0, the origin is a saddle point. In the AD plane, we need d to be negative. Most solutions go away from the origin, so x star equaling 0, 0 is not stable. As t tends to infinity, they approach the eigendirection spanned by the eigenvector v2 corresponding to the eigenvalue λ2. This line is called the unstable manifold of the saddle point x star is equal to 0, 0. The only case when the solution approaches the origin is when they start on the eigendirection spanned by the eigenvector corresponding to the negative eigenvalue λ1. This line is called the stable manifold of the saddle point x star is equal to 0, 0. A solution which is not starting on the stable or unstable manifold approaches the stable manifold when t tends to infinity. Now let's consider when lambda is complex with the imaginary part not equal to 0 and λ1 does not equal λ2. We have that d is greater than a squared over 4, and there are three subcases. If the real part of both λ1 and λ2 are negative, the origin is a stable spiral. In the AD plane, we have d is greater than a squared over 4 and a is negative. These spirals appear because x of t is equal to a1 e to the λ1t v1 plus a2 e to the λ2t v2, but now a1 and a2 and v1 and v2 are complex. If the real part of λ1 and λ2 are both positive, the origin is an unstable node. In the AD plane, we have that d is greater than a squared over 4 and a is positive. If the real part of λ1 and λ2 is equal to 0, then the origin is a center. In this case, d is positive and a is equal to 0. The solutions are periodic in this case. The centers are stable, or more exactly neutrally stable, as they are not attracted to the equilibrium point. Now, let's move on to the borderline cases. these occur on the remaining lines in the AD plane. If λ1 equals λ2 which equals lambda but it does not equal 0, we have that this in the AD plane corresponds to d equaling a squared over 4 and d not equaling 0. In this case, the origin is a star when there are two linearly independent eigenvectors v1 and v2. Any initial condition x0 can be written for some constant c1 and c2 as x0 is equal to c1 v1 plus c2 v2. So the solution approaches the origin on a straight line generated by x0. When there is only one eigenvector corresponding to the double eigenvalue lambda, the origin is a degenerate node, and solutions are attracted, or repelled depending on the sign of lambda, tangent to the direction spanned by the eigenvector. If A is negative, the origin is a stable star, or degenerate node, and if A is positive, the origin is an unstable star, or degenerate node. If λ1 equals 0 but λ2 does not equal 0 but is still a real number, this corresponds to the line d equals 0. In this case, x star equaling 0, 0 is not the only equilibrium point. There is a whole line full of equilibrium points, and the trajectories approach these equilibrium points along some parallel lines having the same direction as v2 if A is negative, or are repelled if A is positive. If λ1 and λ2 both equal 0, then either there is a line of equilibrium points but they do not attract or repel the other trajectories which are parallel to this line, or the whole plane is filled with equilibrium points, which occurs when A, B, C, D are all equal to 0. Then, let's discuss nonlinear systems. We now consider x dot equals f of xy, y dot equals g of xy, where f and g are given functions. We don't expect to solve analytically nonlinear systems. However, we have that different trajectories never intersect. Note that the Jacobian matrix is fx, fy, gx, gy, where fx means the partial derivative of f with respect to x, fy means the partial derivative of f with respect to y, and similarly for g. If we evaluate the Jacobian at an equilibrium point, we arrive at a linear system. We can neglect the non-linear terms in the analysis of the equilibrium points if they are not borderline cases. In other words, if the linearized system predicts a saddle, node, or spiral, then the equilibrium point is a saddle, node, or spiral for the full non-linear system. However, the borderline cases, i.e. centers, degenerate nodes, stars, non-isolated equilibrium points, can be altered by small non-linear perturbation. Now, let's define a conservative system. In the general case, x dot equals f of xy, y dot equals g of xy, where f and g are given functions, the system is called conservative if there is a conserved quantity, i.e. a real valued non-trivial continuous function e of xy is constant on the trajectories dE over dt is equal to 0. In general, we can find a conserved quantity of a system by computing dy over dx is equal to dy over dt divided by dx of dt, which is equal to g of xy divided by f of xy, and using, if possible, the separation of variables. Hence, let's discuss a result for conserved quantities. If E, the conserved quantity, has a local minimum and isolated equilibrium point x star y star, then x star y star is a center, i.e. all trajectories near x star y star are closed. Next, let's define a heteroclinic orbit. A heteroclinic orbit is a trajectory of a dynamical system which joins two different equilibrium points. Then, let's define homoclinic orbit. A homoclinic orbit is a trajectory of a dynamical system which joins a saddle equilibrium to itself as t tends to plus or minus infinity. Now, let's define a limit cycle. A limit cycle is an isolated closed trajectory, i.e. the neighboring trajectories are not closed. If all neighboring trajectories approach the limit cycle is stable or attracting. Otherwise, the limit cycle is unstable or sometimes half stable. Now, let's define a gradient system. If the system x dot equals f of xy and y dot equals g of xy can be written as x dot is equal to minus grad fx, where grad fx is equal to the partial derivative of f with respect to x with the partial derivative of f with respect to y, we call it a gradient system. This means there is a continuously differential scalar function f called a potential function so that x dot is equal to minus grad f of x. We have the following result for gradient systems. In a gradient system, closed orbits are impossible. And, as ever, thank you for watching.